Associated with every linear program is a so-called dual program, which is also a linear program. This definition is most elegant when stated in terms of the symmetric form. Indeed, now you see why this form gets the name symmetric. As we saw in the exercise, the dual program can be thought of as the problem of minimizing an upper bound on the primal program. Observe that for all feasible y, we have that B transpose y is at least y transpose AX. Here we've just used this constraint here from the primal and the non-negativity of y from the dual. And this in turn is at most CTX by the constraints of the dual here and the non-negativity of x in the primal. In fact, we just proved the weak duality lemma, which states that if x is feasible for the primal and y is feasible for the dual, then CTX is at most BTY. That is to say, that the value of the primal is at most the value of the dual. And this makes sense because we built the dual as essentially an upper bound on the primal. Another thing to note here is that if your primal problem isn't in this exact form, you can always convert it and then look at the corresponding dual and simplify. Often, however, it's easier just to remember that the dual is the problem of bounding the primal as tightly as possible. For instance, if we change the primal inequality to an equality, then we can proceed by the same argument, only this first inequality becomes an equality. And I don't have to rely on the y being non-negative. Everything else stays the same.